we are going to now take a look at our first sort of section of stoichiometry. It is called gravimetric stoichiometry. Now, stoichiometry of a reaction is the description of its relative quantities of the reactants and products by chemical amount. Okay, and that's always in moles, so that's important when we're talking about stoichiometry. Now, the procedure for calculating the masses of a reactants or products in a chemical reaction is called gravimetric stoichiometry. Now, please note this is to do with masses. Gravimetric is because of gravity, and without gravity, we wouldn't have weight. And remember, gravity is something that acts on a mass. So through gravity and sort of filtration, we can get the mass of a product or reactant. In terms of a lab or empirical setting, we can use that sort of gravity to filter out any sort of mass in a chemical reaction. So that's kind of where the name came from. But when you hear gravimetric stoichiometry, we're really talking about the masses of our reactants and products in a chemical reaction. So, in order to figure out any sort of stoichiometric calculation, I'm going to run you through the steps here first, and then we're going to look at a few examples. So, step number 1, we write out a balanced chemical reaction and list all known entities. Okay, we convert the mass of our measured substance into moles. So we go from mass to moles. Okay, which is what you see here with our stoichiometric calculations on the side here. We convert mass into moles. Now remember that we can use this formula that if we have moles equals mass over molar mass, and if we're provided a mass, we can convert this mass into moles by putting moles or mass over molar mass to get our moles or our chemical amount. Okay, step number 3 says calculate the moles of a required substance using a mole ratio. Now, this concept of the mole ratio we have seen in our previous units with gases and the law of combining volumes, and we've also seen it a little bit with our solutions unit, but this is where we get really familiar with the mole ratio. Okay, and we get this from the balanced chemical equation. Okay, step number 4 is we convert the chemical amount of a required substance into its mass. Now this is depending all on what our question is asking for us. If we're asking for a chemical amount, we can end at the mole stage. If we're looking for mass, we have to convert it back into a mass. Now, again, with our mole ratio, one thing I mentioned in our lesson on the law on combining volumes in our gases unit is that sometimes we call this the required over given ratio. And essentially what that means is that if we have a required entity, that is an entity that is something we are trying to solve for. If we're looking for our ratio for our given entity, it's an entity that has information that has been provided to us or given to us. So I prefer not to use this formula required over given. I like to think of it as a unit cancellation, but we'll get into that as we look at an example. So let's just jump right in. This says, if you decompose malachite, what mass of copper oxide would be formed? And something just happened here with my sort of notation of my copper oxide. So I'm just going to adjust this first here. Okay, so this is copper. This is just a multiplication sign. So essentially, we are decomposing malachite, which decomposes into 2 copper oxides, carbon dioxide gas. This is something that is provided to you, by the way. It's not something you have to come up with. Okay, and water vapor. So this is a gas, and this is also a gas. Okay, so this is saying, if we have 1 gram of malachite, what mass of copper 2 oxide would be formed? So essentially, I like to use my chemical reaction almost as a table where I organize all the information relevant to each entity. So in other words, I would say, here I'm given my mass of malachite, which is 1.00 grams. Okay, and I'm solving to find my mass of my copper oxide. So I'd like to put a question mark there. Now, another thing that I can put down is I can put down my molar mass of malachite. So my molar mass of malachite, now, again, this is something that I'm going to need to calculate. It's copper plus 2 oxygens, 2 hydrogens, plus another copper, plus a carbon, plus 3 more oxygens. Now, because I'm just trying to save a little bit of time, I'm going to provide you the molar mass of malachite. However, in every other equation, you are going to need to calculate that molar mass. So in this case, our malachite molar mass is 221.13 grams per mole. Okay, and our molar mass of our copper oxide, again, I'll provide this value to you, is 79.55 grams per mole. So, essentially, our first step is to convert our mass of our given entity into a mole value. So our first step is going to be to convert our mass to moles. So we have moles equals mass over molar mass. So this is going to equal 1 gram over 221.13 grams per mole. Okay, so when I do this calculation on my calculator, I get an answer equaling 0.00452 moles. Now, at this point, this is nothing new to you. You have seen this type of calculation several times before, where you're going to calculate your moles from your mass and your molar mass. This is not new. Okay? This next portion, where we use a mole ratio, is, however, new. So what I like to think of this as is, if this is my number of moles, I will write down this is my moles of my malachite. Okay, and I'm just going to write the word malachite because that's a little easier than writing out this entire statement, or this entire chemical compound, I should say. So what I'm doing is I'm going to multiply that by a mole ratio. Now, the way to think of this is that if you think of this as we're decomposing a bicycle, forget that it's malachite. Okay, all that it's saying is that to build this bicycle, we had 2 handlebars, we had 2 tires, we had 1 front brake, 1 reverse back brake, we have a bell most likely, we have 2 pedals, okay, but 1 frame. So essentially, when we break this up, this is like saying we have 2 wheels, which is my copper oxide, 1 frame, and 1 bell. Okay, so each of these entities is a component of our original bicycle. Okay, or in other words, if we were to be baking a cake, I have these components, okay, and these are the ratios. If I bake a cake, I can't put 2 cups of flour and then 14 eggs. Okay, I need 2 cups of flour and 1 egg. So this is my ratio in my chemical equation that makes a perfect cake or a perfect chemical reaction. So essentially, because of that, if I was to say need to make, instead of making an entire cake, I need to make a single cupcake, I'm going to look at how much mass of my flour I need to add to make just a single cupcake rather than to make a full cake. Okay, so this is kind of my analogy that I like to use, and I'll come back to it as we go through. But we have to come up with a mole ratio. If we're dividing it by a certain amount, we have to figure out how small we need to make our ratio, or our mass, sorry. So what I like to do is, if I have malachite, this is the same as malachite over 1. If I put any entity over 1, I could put 1 over 1, I could put cows over 1, no matter what I do, it's still whatever it is on the top of my fraction. So in this case, if I put malachite over 1, it's malachite. It's the same thing. So because I have malachite on the top of my reaction, I need to cancel my units out. Now, in order to cancel units out, I always do the opposite function. So in this case, I have it on the top of my fraction, so I want it on the bottom of my fraction in my mole ratio. For the top of my reaction, I'm going to write down the entity that I'm solving for. So in this case, I'm solving for my copper oxide. So my copper 2 oxide, I write down on the top. When I look at my mole ratio between the 2 entities, I like to write down the number of moles of my entities that I have. This way, it tells me right away that I have 2 moles of copper oxide and 1 mole of malachite. When I figure out this mole ratio, essentially I take this value of my 0.00452 moles, I multiply it by 2 and then divide by 1. So when I get this solved, I figured it out to be 0.00904 moles. So this is how many moles of copper oxide I have. So sometimes I like to write that down too, just so I have this value present. Now, we're not quite done. Because we're looking for the mass of copper oxide, I need to convert this molar value, or my chemical amount, into a mass value. So I'm just going to jot this number down here, 0.00904 moles. And I'm going to solve for my mass. So my mass, then, once I rearrange my formula, is equal to my moles times my molar mass. So my mass is equal to my moles, which is my 0.00. This tells me how much I have of copper oxide, moles. And I'm going to have to multiply my molar mass down here. I ran out of space, 79.55 grams per mole. And when I solve for this, when I get my mass is equal to 0.719 grams. This is the amount of copper oxide that would be produced when I decompose malachite. So, like I said, when we start with a mass, okay, we have a mass and we convert that to moles. And this is using this formula, moles equals mass over molar mass. Then, from our moles, we find moles again using what we call our mole ratio. Pardon me. Mole ratio. Then we convert back to find the mass of our unknown entity by using our mass equals moles times molar mass. So we can use this sort of mathematical square to solve for most of these problems. Let's just take a look at one more example. This says, what mass of iron oxide is required to produce 100 grams of iron? So this is a slightly different type of question, but we can still use the same idea to solve for this. Now, our first step is to ensure we have a balanced chemical reaction. So when I take a look at this, I see I have 2 irons, which I do not have on my other side, so I need 2 irons over here. And I have 3 oxygens plus another 4 oxygens and only 2 over here. So in order to balance everything out, I need to have a 3 here and a 3 here. This gives us 3 carbons, a total of 6 oxygens and 6 oxygens to balance everything out. Now, I again use my chemical equation as a chart or a table to keep my ideas and thoughts organized here. So it says I'm looking to calculate my mass of iron 2 oxide to produce a mass of 100 grams of iron. I also know my molar mass of iron from my periodic table of elements is 55.85 grams per mole. And I know that my molar mass, once I do my sort of basic calculation here to calculate my molar mass of iron 2 oxide, 2 irons, 3 oxygens, gives me 159.70 grams per mole. So when I get this reaction, again, I'm going to start by calculating for my moles. So my moles is equal to my mass over my molar mass. And I wrote that on the wrong side. Mass over molar mass. So when we solve for this, I have 100 grams divided by my molar mass of 55.85. This equals out to be, when I have 100 divided by 55.85, it equals 1.791 moles. So this is how many moles I have of my iron. Now, of course, I have to do a mole ratio, so I'm just going to rewrite this number down here so I have lots of space. And this is moles of iron. I'm going to multiply this by my mole ratio. Again, because I have iron on what's the equivalent of top of a fraction, I want iron to be on the bottom of my fraction here. And I'm looking for my moles of my iron 3 oxide. So I have 1 mole of iron 3 oxide and I have 2 moles of iron solid. When I solve for this and I multiply by 1, divide by 2, or simply just divide by 2, I get 0.8953 moles of iron 3 oxide. Okay, so this is telling me how many moles I have. Now I'm looking for my mass, so because I'm looking for my mass, I jump back over here. My mass is equal to my moles times my molar mass, and my moles I've now calculated to be 0.8953 moles. And my mass is equal to my moles times my molar mass, which is equal to 0.8953 moles times by my molar mass, which is 159.70 grams per mole. I solve this to be a mass of 143.0 grams. Again, I started with mass, I calculated moles, used a mole ratio here, okay, to calculate for my unknown value of moles, and then I plugged it in to my calculation over here, my formula over here, times by my molar mass of my iron oxide to get my mass. Again, this ratio right here is called our mole ratio, and we can call it required over given, or just we can look at unit cancellation. Again, this is what I prefer to do, unit cancellation, but if you like required over given, then the required calculated entity is iron oxide and the given entity is iron, so you can put your required over given, and that can help you work your way through these questions as well. So that is, let's see, oh, not quite. We're just about done for this lesson. So your percent yield then is another calculation that we can do for gravimetric stoichiometry, or any stoichiometry for that matter. And essentially, percent yield is our actual yield over a predicted yield, and this is times 100. So our actual, and sometimes we call our predicted yield our theoretical yield. So based on what sort of calculations we did, and we multiply this by 100%. So if we were to have, say, our actual yield to be 10 grams, but we calculated our yield that we were supposed to get 15 grams, then we multiply that by 100%. So this would equal 10 divided by 15 times 100%. So when we do that, we get equaling 67%. So this is how much we actually got, or how successful our reaction was, based on our calculations. So we had our actual yield over our theoretical yield times 100% to get our percent yield, what we actually got based on what we thought we would get. So this is the end of gravimetric stoichiometry. I would definitely recommend taking a look at some practice questions either online or in the textbook prior to completing an assignment. And if you need to go back and take a look at the 2 examples that we went over in this lesson, I would suggest doing that now. Good luck.